Yeah, that's true. That's true. But actually, there is a more intuitive explanation of this, which is, let's say we have x of n, c0, x of n minus 1, c1 and so on, some value. Let's say it's an nth order FIR filter. This is what we'll have. This is y hat and this is e. And from this we actually take the sign of e. That is, we simply look at whether y is greater than y hat or y is less than y hat. That's the only information that we'll use. So let's say, let's say you are doing this from scratch. Obviously I know the solution, so I'm not doing it from scratch. But if you are doing it from scratch, potentially you could derive it based on logic. Okay. So let's say if e is positive. Okay. This is the information that we get by taking the sign of the error. That means this is the same as saying y is too large, isn't it? Y is larger than what it should be. That's what is the meaning of, that's the meaning of e being positive. Then what do I do? How would I adjust these coefficients? So what I could try and do is, for each coefficient, I try to, if y is too large, if y is larger than what it should be, I try to reduce the contribution from each of these branches. So how would I do that? So if v is greater than 0, I need to reduce the contribution of all branches. So to reduce the contribution, this is not reduction in magnitude, but just reduction. Okay, should become less positive or more negative. That's the idea. So then I look at x. If x is positive, then the contribution here is positive. So I have to reduce the value of C0. But if x is negative, I have to increase the negative contribution. So I have to increase the value of C0. Okay, that is, if x of n minus k is greater than 0, I reduce Ck. If x n minus k is less than 0, I increase Ck. Okay. So basically I know that y is too large, so then I adjust every branch contribution to be something smaller than it was. Okay. Then in the next step I do the same thing. I look at if y is too large or too small, and then I move the contribution of every branch in that particular direction. And in this case the step size is fixed. So in fact it's not just reduce Ck, it's reduce Ck by some fixed amount mu. Okay. At least the equation in the form that we wrote, this is what the meaning is. Okay. And if I write this in equations, I will get Ck in step n plus 1 to be in the step n minus mu, and I subtract mu if e is greater than 0 and x of n minus k is greater than 0. So that is sine of e times sine of x of n minus k. Is this okay? So in fact this is easier to remember, and from this you can remove the signs and get the equation for the full LMS algorithm. That's what the LMS is also doing, but of course it's a proper mathematical way of doing it, where you try to see that there is a global minimum and you drive the system towards the global minimum. Okay.
We have access to such FIR filter. Why can't we generate another FIR filter with coefficients that pass so many inputs and use that to filter out the error that passes to the coefficient?
If we have access to an FIR filter, we have access to these inputs. What do you want to do?
An FIR filter would have so many inputs for the coefficients.
Yeah.
We need to generate those coefficients, which can be done by filtering out the input.
How?
Because E of n is x of n minus k.
Yeah.
So if we convolve E of k
Yeah.
with x of k,
Okay.
we get all those coefficients.
No, that's what we are doing here, right? What's the difference between what you are suggesting and what's happening here? No, actually I didn't quite understand.
We don't need to go for the sign implementation. The difficulty there was to generate E into x.
Yeah.
If we instead put a filter which generates that, well, what would be?
No. Okay. You are saying somehow you got rid of the multiplication. But, and the coefficients of this filter are x. So how do you get a filter with coefficients of x without multiplying it? You are saying, yeah, what the suggestion is, this equation represents, first of all we are looking at E at a particular instant. We are not looking at the sequence of E. But it probably works the way you suggested also. He is saying you pass E through a filter whose coefficients are x. But to do the filtering with coefficients of x, you have to multiply by x. Right? So it's the same thing. In fact, you'll need more multipliers in that case.
So what is the difficulty in implementing that?
Which one?
The multiplication.
So we are not trying to do the multiplication, right? At least in the sine case, we got rid of the multiplication. What is this? How do you implement this? Sin e times sin x 1 minus k? XOR gate. No, you don't need like if you have two logic levels, I mean basically if you have binary logic and you want to implement a multiplier, that's an XOR, right? So I don't know if I answered your question. Actually, I didn't fully understand it. What I interpreted it as was you pass E through a filter whose coefficients are x. But to do that, you have to multiply E with x. Okay, that's what we don't want to do. That is, I don't want to implement full multipliers. So this is the logic behind the sin LMS algorithm, and it works quite well. You can also test it out in the assignments. That's a global minimum because error is a quadratic function of C. Okay. So in the simple case, we saw that in the simple meaning in the one coefficient case, which is a gain control, we saw that E square is what was that? C naught x this, right? So like it's a quadratic in C naught, so it's a parabola, it has a global minimum. Similarly, if you take multiple coefficients in each of it's a second order term for each of the C's. So if you take two coefficients, you will get some complicated expression, but if you plot the shape, I think you're probably familiar with it, it will look like this parabolic cup. Because it's a second order stuff, it will be a global minimum. Is that clear? The question is, why is it a global minimum? Why don't we have, as we plot E square with respect to the coefficients, there could be many local minima. If you do have that, when you drive it with the gradient, it can settle to some local minimum and stop there. But that won't happen because the equation is second order in C. Okay, it's a quadratic equation in the C's. If you have more C's, you will have other C's also, but the highest power of any coefficient will be 2. So in the two-dimensional case, if you have C0 and C1, it will be some kind of parabola. So I think you know what I mean by this. So the cross section of this will be an ellipse. So we had different choices. We took the full multiplication, that is E times x, or you can take E times sine of x, sine of E times x, or sine of E times sine of x. What's the difference between all of these? Besides the implementation effort. Of course, the reason to go to sin LMS was that implementation wise it is simpler, much simpler. Okay. What happens? Will they all move the coefficients in the same direction? All those algorithms. So we had 4 choices, right? What's the difference? One is, of course, the step size will be different. Clearly here, so again I forgot the mu in these cases. So in this case, the step size is always mu in the last case. Okay, and in these cases, it depends on the value of x. That is true.
In the fourth position, freedom was using the step sizes, but independent of the x and the.
Yeah, that's correct, because it's a fixed step size. In the other cases, it depends on the value of x and e. So that is one thing. So that means that the magnitude of the movement is different in the 4 cases. What about the direction of movement? Direction is the same. So let's see. If we have an nth order FIR filter, we have n equations, that is uppercase n equations like this. Okay. Now I can instead of representing it as an equation in terms of each of the coefficients, I can change the coefficient to a vector and write something like this. Okay, not ck. This vector c is nothing but c0, c1, c2 up to cn minus 1. That's all. So again I wrote the vector c at the instant n plus 1. You understand what this vector is, right? It's just the whole set of coefficients I treat it as a vector, that's all. Minus mu e of n, this is just some number, a scalar, and this x is also a vector. In this case, the vector x consists of x of n, the shifted versions of. So essentially it's saying the coefficient vector at instant n plus 1 is the coefficient vector at instant n plus some other vector. So this is the case for the full LMS. Okay. So now you look at this and tell me if the direction of movement will be the same. If it's the same, for which it will be the same. So you understand this, right? I can, so let's say I had 2 coefficients, then it's easy to represent. I will have C0 and C1. These are basically, this is the plane, and the coefficient vector was probably here, let's say at n, at the instant n. Then let's say this is another vector that turns out to be in, let's say, this direction. Rather, let's say this is the coefficient x, or coefficient mu e times x, and this is the coefficient, this is a vector c of n. So then I have to subtract this from this, so I go back like this. So this is where I land up. Okay. So what I mean by the direction is, so somehow on the next instant you again calculate the calculate this vector and move it by that much. Okay. So that's how it, maybe the optimal coefficient is somewhere here, it goes and reaches that. So what I was asking was, will all these four things take the same trajectory, or will the direction be different? First and third will be the same. Why?
Because all of them have the same coefficient multiplying the whole vector.
I don't know if is the question clear? It's not clear. If I represent the coefficient of the vector, I can't do multiple dimensions, I will do for two-dimensional vector. That is, in this case I have C0 and C1, and this also I have x1 and xn minus 1. Okay. Now maybe the optimal value is somewhere here. That is, for the optimal filter, the value of C0 is this much and C1 is this much. So of course, maybe to start off you are somewhere here. The value of C1 is too much, the value of C0 is too little. Okay. So in that case I can say this is the coefficient vector. Okay. That is this. Now what do? I have to look at this vector mu e times x. Mu e is some scaling factor, and let's say the coefficient vector, the vector x at this point is something like this. Okay. I mean, I am not representing the size, I am just showing that x is here. This is the vector c, this is x. So what is c minus x? So from here I go in the opposite direction to x. So now this new vector, this is c minus x, sorry, let me not say this is x, this is x times mu times e with the scaling factor. So this is x times mu times e. Okay. So, and similarly it will take many steps and come somewhere close to this one. Okay. The question is, now this is the equation for the first one, where I take the product of x and e. Will the direction of movement of the vector be the same for all of them? Yeah, here the direction of this is basically the opposite to the direction of the vector x. So I wrote for the full LMS, it was the vector at the instant n minus mu e times the vector x at instant n. Okay. The x consists of shifted versions of the input. Maybe I should use a different, maybe I'll make this uppercase x or something. Okay. Now if you use in fact to avoid confusion, let me make this the vector w in general. So this is how it is. Now for full LMS, which means I am not taking the sign of the error or the sign of the gradient, the vector w is x of n, x of n minus 1, x of n minus n plus 1. I can take this, or I can take mu times sin of e times w. Okay, this is the case where I am taking the sign of the error but not the sign of the gradient. Now when I take the sign of the gradient, I will have a similar equation. So let me call this vector z just for change of nomenclature, and this will be the sign of vector consisting of sign of the shifted versions of the input. Is it okay? Or I can take mu times sin of e times z. Okay, I mean this is more clearly written than previously. So see, the vector w is x of n minus 1 and so on. So let's take again a two-dimensional case. This is x of n. This is x of n minus 1. Okay. So maybe the value of x of n is smaller and xn minus 1 is larger. Okay. So the vector x has this direction. Now what happens if I take a corresponding z? Sorry, this is the, so this is the vector w, that's it. Okay. If I take the corresponding z, the magnitude of these two is the same. Okay, so it's in the same direction of x of n, but I take unit magnitude and I take unit magnitude here. Okay, so the direction of w will be, the direction of z will be different from that of w. I have normalized each of the components, right? So in this case, each of the components has the same magnitude. It's just whereas in w, each of the components can have different magnitudes. So the direction of w and z will be different. I am not saying x of n and x of n minus 1 are different. So let's say you form a vector with xn minus 1. This is one vector. And another vector is sine of xn and sine of xn minus 1. So if you think of this as the x component of the vector, this is the y component of the vector. Similarly here, the second vector is at 45 degree angle always, right? Because it has unit magnitude for each of the components. Whereas the first one can have any angle. Okay. So the direction will be different. So if you take the sign of the error, it won't change the direction. It will only change the amount of stepping, right? It will always, so in this case, the coefficient c is moved in the direction of coefficient w, but the step size is mu e in this case and mu in this case. Okay. Whereas here, the coefficient c is moved in the direction of z, which is different from w. Because you have normalized each of the coefficients by taking you have normalized each of the components of z by taking just the value of it. Just the sign of it.
No, but this is true only if both of them have the same error at one point of time.
No, that's what I am talking.
And then they will diverge.
Huh?
And then after that they will start differently.
Yeah, that's correct. I am talking about a case where you have a certain coefficient value and a certain input. Let's say you didn't have any LMS going on, right? So the system is running and there is a filter and it has some input, and that is, of course, now there is no question of which algorithm you are using. Now I have two identical systems with two identical inputs. One of them I start off with the full LMS, one of them I start off with the sine. Which way will they move? Maybe in the first step. So because of this, there is some complication in using the sign of the gradient. I actually forget the result. I don't think it fails to converge, but it can take a longer time to converge because it's moving in a different direction than the optimal. Okay. How did we come up with the LMS algorithm? We had the error as a function of the coefficients, and we decided to move in the direction of the gradients. Okay. So that will lead us to the global minimum. That was the thought. Now you see that when you take the sign of the gradient, you are actually moving in a different direction. Okay. You don't move in the opposite direction, but you move in a different direction from that. Anyway, I will confirm that result. I don't know if there is a failure to converge, but it should, I think it takes a longer time it can take a longer time to converge. So if you interpret the coefficients as vectors, then at each step you are moving the vector in the direction of the gradient vector. Now the gradient vector in the full LMS case, it is a vector formed by the shifted inputs, and in the sign, when you take the sign of the gradient, it is the vector formed by sign of the gradient, sign of the shifted inputs. So the two have different directions. Okay. Now taking the sign of the error is a very benign thing. It only changes how much you move in that direction. So in this case you always move by mu, in this case you move by mu times e. So as the error gets smaller, you move less and less. That the effect of that we discussed yesterday. So the result is when you take the sign of the error, you end up not converging to the absolute minimum, but you keep bouncing between on either side of the minimum. Yeah? How? See, the direction is governed by this, right? So the value of mu will only scale how much you move. For instance, so in this case maybe you will move by this much, or maybe you move by this much, or maybe you move by a little less. That's the only thing that you can adjust. Why? With the coefficient mu. Okay. The direction you cannot adjust with the coefficient mu. Is that okay? Any other questions on this? But actually this is in fact this turns out to be, we will see the math later, that simplification of the proper LMS. So when you minimize the least mean square, you have to take the mean square. That is, you have to minimize the expectation of E square. In this case, we kind of ignored the expectation and went with the gradient of E square with respect to C. This is a great simplification for practical realization, and it works very well. So if you had to take if you really have to minimize the mean square error, you have to look at the time average of E square or the ensemble average of E square, and then try to minimize that. You have to take but that takes a long time and lot more effort to do. Anything else about the LMS or the sin LMS? So there are some other practical issues with the LMS algorithm. The first thing is, the way I wrote it was C of n plus 1 is C of n minus u times E times x, okay, where x is the shifted version of inputs. Now, one thing is, you don't have to update the coefficients in every step. Let's say you are operating at 1 gigabits per second. So your sampling rate is sampling period is 1 nanosecond. You don't have to update the coefficients for every 1 nanosecond. In fact, that may be not so desirable. You update it at a much lower rate. That is fine, because the changes that you want to track are slow. What's the implication of doing it slowly? So what I'm saying is, let's say the input x is coming every 1 nanosecond. Okay. So at every instant you have the vector c and vector x. So between this point and this point you can update the vector c, but you don't have to do that. You can keep the same vector c up to this, and then at this point you update it to the next value, and so on. Okay. So you update c infrequently compared to the data. The data is changing every 1 nanosecond, but you don't have to change the coefficient c every 1 nanosecond. What are the implications of doing something like that? Why would we want to do? Power will be less. Why? Now, of course, if you update the coefficient slower, you can only track slower changes. Okay, but still, you don't expect the channel to change generally within 1 nanosecond. That is usually not the case. Okay. It's not so much the change of the channel, but the changing data itself. You don't want the coefficient to be chattering around so much. That's usually the case. And also, the important thing is the power dissipation. Even the simplified sin LMS does take some power because it is some digital computation. Each coefficient you have to compute and feedback. Even though you have reduced this part to a single bit XOR, this part is still multi-bit. That is, the coefficients are some digital words. Each coefficient is a digital word, right? It's not very long. It may be like 5 bits, 8 bits, that type of stuff. But still, to do that computation in every cycle takes a lot of power, and it's completely unnecessary because you don't expect anything to change over such a short time interval. Okay, so you can update the coefficients far less frequently and still do a good enough job. So you don't update the coefficients very frequently. So the way I wrote it was, this is Cn plus 1 Cn, and this x vector was x of n minus 1, and so on. So, but the update of C does not have to happen at the same rate or the same period as the update as the changes in x. Okay, so you do it much less frequently. Is this clear? So maybe let's say every 1000 instead of doing it every 1 nanosecond, you will do it every 100 nanoseconds. Okay, you change the coefficients only once every 100 nanoseconds. You still have to form the vector x with shifted versions of this one, where these are data in successive 1 nanosecond periods. Okay, it's just that this n plus 1 and this n refer to much longer intervals. Okay, I can make a different notation for it, but I think you get the idea, right? So let's say I want to update the coefficient at this point. I look at the values of x, the relevant vector x, that is the shifted version of the inputs at that point, and then based on that I update the coefficient here. Then for another 100 cycles I don't meddle with the coefficients, so I update it afterwards. So this is typically what is done. This is mainly also to save digital power, because if you have a long equalizer, in fact in some cases you can have very long equalizers, like for the gigabit Ethernet cards, the equalizer in that has of the order of 100 taps, 200 taps, and so on. So to update, so basically each of these coefficients has 200 elements, and you have to update that. If you want to update it in every cycle, that's a huge amount of power. Okay, you certainly don't want to dissipate that much power. So you slow down the adaptation. And it works well enough because adaptation anyway is required to track out the slow variation. So another issue is the value of mu. Okay. So let's say, so we had our variable current source. Now this was for the equalizer in the transmitter. So what we did was, let's say you put multiple transistor here and switch them to get a variable coefficient. Okay. Now this was for the coefficient in the transmitter, but let's say for the receiver also we have done something similar, right? And what is the value of, and let's say I am using sine LMS. What is the step size? Mu of each coefficient. And if I want to reduce mu, what do I have to do to the structure? No, not reduce the coefficient, reduce the value of mu. The update of each coefficient and any step is mu, right? How can I reduce the value of mu? Let's say I find that the value of mu is so large. So firstly, if the value of mu is very large, it can have non-convergence. But even if it is convergent, you don't want a case where, let's say for the single coefficient case I showed that. So firstly it can be non-converging, but maybe it is not that bad. But finally, if the mu value is large enough, it will go from this value of error to this and then back to this and so on. So it will keep oscillating between these. But with a smaller value of mu, it may move lower down on the error. Okay, this is the error. This is the magnitude square of the error. Okay, so if you have a large value of mu, it will oscillate between higher values of error. It has to, right? Because the step size is large. So it has to, it will bounce around between two values of coefficients or more. Two values of the coefficient or more. So the smaller the value of mu, the smaller the error that you will have with the sine LMS. Is that okay? With the full LMS, the value of E itself gives you the step size. It is the value of mu times E. Okay. So as the error gets smaller, the step itself gets smaller. Whereas with the sine LMS, the step is always mu. So if the value of mu is very large, the final steady state error will also be large. So you want to reduce the value of mu. Yeah, so you can do that. But what is the limitation there? So you see, to reduce the value of mu, you simply have to have more steps in this, right? Because in this case, I go from having one transistor to having two transistors, three transistors and so on. So the step size is limited by how many pieces I have split this transistor into. So I can keep on splitting it into more and more pieces, but beyond some point it becomes not practical. In fact, with this kind of realization, maybe 5 or 6 bits is the maximum.
How do you start with a whole value and try to, you will have a range. Start with a low coefficient, then we will have a range. How do you know the final C will be within the range?
Oh, that is okay. We have to a priori decide what are the channels we want to adapt with. So perhaps you can do this in MATLAB if you do have the channel models. So you look at the length of the equalizer that you need and also the range of coefficients. And then you make your equalizer such that you cover those values of coefficients. So like I said, you can always find a channel that will break the equalizer or the adaptation, right? You can always, it's not very difficult. You just take something of half the bandwidth of what you normally use and it will probably break the equalization. So if you have a large value of mu, it will keep chattering around with a large step and that can give you a large error. Okay, it's not just this steady state error. It's just a changing value of coefficients is not a desirable thing to have. So I shouldn't say how would you reduce the value of mu, but how would you reduce this chattering around? Because if I implement this, let's say, so this is the equation I will implement for the coefficient Ck, the update. Okay. Now this coefficient will be changing in every step because I get some sign for E and some sign for X. So it will constantly be either increasing or decreasing. I mean, not constantly increasing or decreasing, but each step it will be bouncing around. Okay. How do you reduce that? So let's say the coefficient is near the coefficients are near the optimum. So what will happen in one step, time interval, it will increase by mu. In the next one, it will decrease by mu, and so on. That's what will happen, right? Because the sign of the error is changing sign. The sign of the error is opposite in each interval or something. But you don't want that kind of coefficient bounce. How can you reduce this? Take the average. Yeah, that is what you have to do. So that is, you look at this product over a long time. Okay. So if it shows a trend, that is, you just simply accumulate this product. Okay, you put this product sin of e times sin of x minus n minus k through to an accumulator. Now, if the coefficient is somewhere here, definitely it will show a trend of increasing, or decreasing, and if the coefficient is here, it will show some trend of decrease. But if it is here, the accumulated value will be 0. Okay, so you integrate this, or you accumulate this product of sin of e and sin of x, and only if it hits some threshold, you increment the coefficient. Okay, so that way you will not have chatter when the coefficient is near the optimum, but it is just bouncing around the optimum value. So what happens is, let's say the coefficient values, if you look at it closely, initially it will have some behavior, but in steady state also with the sin LMS, maybe the optimum coefficient is here, but then the coefficients themselves are quantized, and the quantized levels may be here and here. So it will keep bouncing around, and you don't want this coefficient bounce. Okay, that tends to also increase the error. So what you do is, if in this case, you would just rather keep the coefficient to be constant, and you achieve that by averaging this sin of e and sin of x. Okay, so only if sin of e and sin of x is constantly positive, that means that the accumulated value will keep ramping up and hit a certain threshold. Only if it hits that particular threshold, you decide to decrement the coefficient. Okay, similarly on the other side. So you don't, although this equation says you look at the instantaneous values of e and x, you do an averaging so that the coefficient variations in time are smoothed out. And also it gets rid of the effect of noise. Although, I mean, here we look at the sin of e and sin of x, like each of these also has some noise in it. Okay, and because of that, the coefficient movement, there will be some movement in the coefficients. You want to minimize that as well, so you do averaging over a long period to get rid of that. Okay.
Surely the noise is reduced when we take the sign.
Huh?
Surely the noise is reduced when we take the sign.
Yeah, but the noise can make the sign opposite, right? So whatever is a small positive error, it can turn it into a negative error. In fact, in that particular case, you can think of it as having amplified the noise. Maybe the noise is also small. It went from just being positive to just being negative. But because of this, it takes a large step downwards. Any questions on any of this? So these are practical things that you have to do. Firstly, you have to operate it slower so that you don't burn so much power in the adaptation engine. And secondly, you also do averaging so that you don't get a lot of chatter in the. So you move the coefficients in the direction of the gradient. Okay, that's the basic principle. You use sin, that is, you take the sign of the error on the sign of the gradient, or at least one of them, to simplify the coefficient update. And the coefficient update itself is run at a lower rate. When I say lower rate, it's lower rate compared to data. So this is not much of a compromise, because anyway you don't expect variations at the data rate in the channel. Okay, at least for typical cases, this adaptation is supposed to take care of, firstly, if you have different kinds of channels, in which case at the startup it has to compute the right coefficient, and also any slow variation inside the chip itself or in the channel, it's supposed to take care of. Okay, so as the chip heats up, maybe its gain and bandwidth reduce, and the adaptation is supposed to take care of it automatically. Then also average the product, average the sin product before updating CK. So these are all some kind of practical things. Maybe you take average over hundreds or thousands of values. Okay. So it's a compromise between, because this also slows down the adaptation, right? If you take average over a long interval, it slows down the adaptation, because instead of let's say sin of e times sin of x is positive, you would have normally decremented the coefficient, but now you decide to average by 1000. That is, only when this accumulated value reaches 1000, you decrement it. So now the adaptation is slower. So it's a kind of practical compromise. So it depends on totally on the practical situation, how much time you have. This is not? No, x of n. So in this case, that's why I'm talking about adapting the receive equalizer, right? So I do, right? I do have access to X of n. No, I'm not. So X of n is the input to the filter. Sorry, X of n is not the transmitted signal.